so we're going to start off with this. First two bullet points here is what we basically talked about so far when referring to acids. Acids dissociate in water to make hydronium. Hydrochloric acid is an example of a strong acid. Next class period, you are going to be learning how to identify, just by looking at the formula of the substance, whether or not it's a strong acid. I mean, quite frankly, there is only, I'm trying to think here, 7 or so strong acids total, so you could almost memorize them if you really wanted to. But next class period, you're going to work on a packet that's going to show you how to identify, just by looking at the formula, whether or not it's strong. Notice in this equation of my second bullet point, it is an arrow only going towards the products, meaning that this will completely dissociate. The H plus and the Cl minus will separate from one another. Because again, this equation could just as easily be written as HCl. Oh my goodness, that is not calibrated at all. Makes H plus and Cl minus. Fix that later. Again, you can omit the water if you wanted to. Now, my second two bullet points. The vast majority of acids out there are not strong. They are weak. They only partially donate that hydrogen. So in that case, acetic acid is what I'm showing you on the very bottom bullet point here. That's the acetate polyatomic ion with the hydrogen on it. Now, it would only donate this hydrogen. So first off, when we look at the formula, yes, I see 4 different hydrogens in acetic acid, but at the same time, the lead hydrogen is meant to show you, hey, this is the one that will actually be dissociated, that will actually be donated. However, it can't completely grab hold of this. I mean, you'll learn next class some of the reasons why bond length is part of it. They might talk about electronegativity as part of it as well. So there's a couple of reasons why some things like HCl can completely donate that hydrogen, so it's almost ionic-esque. Some things like acetic acid don't. Double arrow. One of the dead giveaways is, hey, this has to be a weak acid. So all comes back to equilibrium again. So we're definitely going to be hitting upon equilibrium, and that's where the math that we did to warm up with today, we can't forget. But today, we have to tack on a little bit of equilibrium stuff before we do the math that we did. All right. Well, I suppose, because it's not calibrated. There. Bases, same story. Some bases are strong. Like sodium hydroxide, it completely dissociates in water to make that hydroxide ion. Therefore, we could do that calculation that we did up on the board for letter B to warm up class here. Because if you know the molarity of NaOH, you know the molarity of hydroxide, the polyatomic ion that makes it a base. However, a lot of bases don't completely dissociate. These are typically going to be the ones that are not just ionic, like Na plus OH minus. Ammonium hydroxide is an example. This is one that we're going to be working with in the lab. Actually, I have 3-liter bottles of it back here to prepare for some of the labs that we're going to be doing a little bit later. It only partially dissociates. And again, for my second bullet point, I just wrote water above the arrow to show it's dissolved in water. Unlike the ammonium hydroxide, or there's other bases like ammonia, NH3, that can just react with the water as well. So, if you are a strong acid or a strong base, you will dissociate. That means you'll create more products. Some of these almost completely dissociate. They completely make their products, like your HCl example. However, weaker acids and bases do not form much of the product. It's going to be a little bit more of an equilibrium where you're going to have some product present, some reactant still present. There is varying levels of weakness. So some things are weaker than others. Over the course of the next two class periods, both numerically with an equilibrium constant, and by looking at the structure of it, which is what we'll do next class, you'll be able to tell what acid is weaker than another acid. Again, the same general principle goes for bases, although next class our focus more is on acids. Okay. The last thing I have to bring up with this first batch of notes is something that's referred to as conjugate acid-base pairs. When dealing with, in particular, these equilibrium type reactions for weak things, however, it could be for strong things as well, we need to get used to identifying the acid and what it turned into, its conjugate. The base and what it turned into, its conjugate as well. This vocabulary you're going to see on the website tonight is a simple, hey, here's a formula of an acid. Show me what its conjugate base is. But when we get into the topic of buffers, which will be next week, we need to be familiar with this vocabulary. And actually some of the math that we do will take advantage of this as well. So first off, again, my first bullet point states that a conjugate base is on the product side of our equations I showed you before. And it's the part of the acid that remains after it lost a proton. Conjugate acid, on the other hand, is on the product side, but it's the base that gained a proton. Here's the example I'm going to give you. HF is hydrofluoric acid. It is a weak acid. As you will learn next class, it is the only halogen, that being fluorine, that is, when it's bonded to hydrogen, a weak acid. Because all the others, HCl, HBr, and HI, are strong acids. And if I were to look at this equation, I should be able to identify within this reaction what reactant is acting as the acid, what reactant is acting as the base, what product is acting as the acid, which will now be called its conjugate acid, and what product would be the conjugate base. And here's how I'd label those. I would recognize that HF in this case is acting as the acid because it donated a proton. Water, again, depending upon water, what it's around, water can act as an acid or act as a base. It's amphoteric, kind of depends on what it's around. Water in this case was acting like the base because it was accepting the proton, going back to that Bronsted-Lowry definition. So I can label my reactants as one's an acid, one's a base. On the product end, partially to keep products separate from reactants, we put the conjugate, the C, in front of these two labels. H3O+, I mean, that is kind of the definition of what is an acid. So this is our conjugate acid on the product end. Otherwise, it's the base after it gained a proton. The conjugate base in this case is the fluoride, anion. What is left over of the acid. This identification is the first skill thing that we're going to practice today. So if you can have out that sheet of paper you picked up on the way in that has you label these things, let's spend about 5 minutes practicing this right now.